Problem 412 brings us to a member in bending and gives a cross-section as such. It gives dimensions of this member of the top flange is 36 millimeters thick, and the rest is 108 millimeters high, with a width of 72 millimeters. And a flange width of 216 millimeters. And the centroid is pre-calculated for us at 54 millimeters. Also given for this problem is at the moment, at this point, is 6 kilonewton meters, and since everything else is in millimeters, I'm going to do the same here, multiply by 1,000 millimeters over a meter, so I've got 6,000 Newton millimeters. And this moment is about the x-axis. Okay, so we'll draw in our x and y axes here. Here's our y. Here's our x-axis. Now let's see what we were trying to find. We were trying to find the force on the top flange. So this top flange has this kind of area. That's all those top flanges, is this area. And here's our, there it is. So this area is taking a certain amount of load. So that will give an indicator of what we need for our equations. So the equations we're going to use are as follows. Well, we need to have the stress at any given point in a member under bending. So that's m times y over I. And also the force is equal to the integral of the stress times the area. Now for this equation, I want to check up on what we have. We've got the bending moment, that's given. Y is a variable, so we'll just use that in this equation here. And I is the area moment of inertia of the entire cross section, entire thing. So we will need to calculate that. So we'll set up our equation here, and so we have f equals the integral of m times y over I times dA. And since the bending moment is a constant and I is a constant, I'll bring those outside the integral. And going to break down dA as follows. The area in question is up here, and the area is of any thin section here's dy. That thin section of dy will always be multiplied by the constant of 216 millimeters, which we'll refer to as the base of the top section. So base 1 times dy. Now that base is also a constant, so I take that outside. M times b1 over I times the integral of y dy. And we're going to go from this is a equation here. The y is the distance from the centroid to whatever point you're interested in. So in this case, we're starting at the bottom of the top flange, which is 18 millimeters, 54 minus 36, from the centroid, and going all the way to the top, which is 54 millimeters. So we'll have an indefinite integral from 18 millimeters to 54 millimeters, and so we'll be integrating m times b1 over I and y dy, and that's going to end up with 1/2 y squared from 18 millimeters to 54 millimeters. So back to what we have and what we don't. This is given, b1 is given. Only thing we need to do is calculate I. We're going to break this cross section up into two sections. First is going to be the top. Second is going to be the bottom here. So we've got two rectangles, makes it fairly easy. And so the I of the entire cross section, IT for total, is going to be the area moment of inertia of the first as if it was by itself, plus the moment of inertia of the second as if it were by itself, plus we have to consider the parallel axis theorem for each. So it's going to be the area of the first times its distance, the distance of its centroid to the system centroid, the full centroid, at that 54 millimeter mark, squared, plus area of the second part times the distance from its centroid to the centroid of the entire cross section, and that quantity squared. Well, the area moment of inertia of a rectangle by itself is bh cubed with respect to the horizontal axis where we have our loading. So our bending is going to be about that horizontal axis. So it's going to be b1 h1 cubed over 12 plus b2 h2 cubed over 12. Then we have to consider the parallel axis theorem, plus area of 1 is b1 h1 y1 bar minus big Y bar quantity squared plus b2 h2 y2 minus y bar 2 minus big Y bar squared. Alright, now that we've got these values to plug in, for the base of 1 it's 216 millimeters. The height of 1 is 36 millimeters. Base of 2 is 72 millimeters, and the height of 2 is 108 millimeters. Right. So got 216 millimeters times 36 millimeters cubed all over 12 plus 72 millimeters times 108 millimeters cubed, the whole thing cubed, all over 12. Okay, those two set up. Now these two, again, the base of 1 and the height of 1 are given, and we need to find this distance, where the centroid of each of these is. So the centroid of 1 is in its center right here. It's 36 millimeters down. Its thickness is 36 millimeters down, so that means it's halfway, which means it's 18 millimeters from the top. And this difference, 54 minus 18, is going to be 36 millimeters. So write that in, plus B1 is 216 millimeters times 36 millimeters times Y bar 1 is 18 millimeters minus 54 millimeters, and that quantity is squared. Now we have to enter in the parallel axis of the second term of the second section, and we have the base 2 and the height 2 again is 72 millimeters times 108 millimeters. But now what's this difference? Okay, we've got big Y bar is 54 millimeters from the top, but what's the distance of the centroid of the second portion from the top? Well, we have to take this 36 millimeters and then add half of the height here, which happens to be 54 millimeters, half of 108. So we've got 36 plus 54 is the little Y bar, millimeters minus the big Y bar, which is 54 millimeters. And that whole thing gets squared. Alright, once all these calculations are done, we find a total of 28.6 times 10 to the 6th millimeters to the 4th, and that is our I total. That's the bottom part. So that's a lot of the hard work here. So to finish up, put all these numbers in. M is 6,000 Newton meters. B1 is 260 millimeters. B1 is 216 millimeters. And that's all over 28.6 times 10 to the 6th millimeters to the 4th, and all that's times 1/2. And this, I'll plug these values in for Y, and we have 54 millimeters squared. Let's take a look better. Minus 18 millimeters squared. And our units, I forgot the kilonewtons in here. Our units end up with kilonewtons times millimeters times millimeters times millimeters squared. So we end up with kilonewtons times millimeters to the 4th, and all over millimeters to the 4th on the bottom. And our number is 58.8. These millimeters to the 4th all cancel out, so our final answer is 58.8 kilonewtons.